So let's go. Let's start the presentation. Thank you everyone to be here. I'd like to ask you if you have some questions at the end. You can chat and we try to answer the questions that you have. And also after this presentation, we will send you some feedback, some questions to understand a better way to improve our presentation. So let's start here. So the idea today, we present you a nice work which integrates the different areas of simulation. For example, static analysis, optimization, casting simulation, also fatigue analysis. So my name is Velmer Fleischmann. I'm a mechanical engineer. I have been working with more than 15 years with simulation, with a lot of softwares, and I'm the business manager and engineering manager at Virtual.PYXIS. So structure optimization promotes the reduction of costs of manufacturing, as we have a lightweight design, so the components we get are lightweight, so we can save some money about material. But after the optimization, it's necessary to validate these components following standards and procedures. And one of these standards most of the time is talk about fatigue evaluation, which is kind of cycling situation. You have a cycling load from to apply to your component. So you also most of the time are invited to check this fatigue component evaluation. And for the situation of a new component, you also, it's important in the case it's a casting process situation, you simulate also this, trying to understand the better way to get this information from this casting process and use this information later on to the durability behavior and durability analysis. And it's true from the casting process, you can take this information. You see that, for example, we can take some properties to, for example, the tensile strength of the material, which will vary from part to part of the component, and also this affects the fatigue results, why the endurance limit of the material is related to this variation of the tensile strength. So here is the workflow we have used for this model. We start. So here, as I was telling you, that we had the evaluation of the static analysis using ANSYS, and after that we got the first validation from the FEMFAT model, which is from this part, this situation, we didn't take any properties of the process. After that, we went to MAGMA simulation, and with this MAGMA simulation, we sent the new properties to FEMFAT. So before I forget, I'd like to thank you, the people from MAGMA Brazil, especially Schmidt in Luciana. They helped me very much about this MAGMA simulation. It was very important working together on this model. So what's topology optimization? For perhaps for someone it's a new term. Topology optimization, we start from this kind of extended design, and at the end we can get this different design, which is sometimes very difficult to reach with our experience. And of course that here is a free manufacturing condition, but you can apply different manufacturing conditions, trying to get the best design. And today we can have more applications also about the topology optimization, because there's a new trend of the 3D printing, and for some components, and these components, for example, they're more free for this manufacturing, for example. Optimization model, this is a real model from engine mount support. So here you see the model. We create this extended design, and there are some screws here for and we also represented some cutting part of the engine block to get the best stress distribution for this region, for example, which also will give some stress and strain around the both regions, and so that's why it's important to consider this part. So here is some areas of our model that we didn't change because they are in contact with bolts, for example, and here is also in contact with parts of the model where we apply the force, for example, and also some parts which are in contact with the engine block. So these parts, the optimization cannot take material away, for example. So this is the condition for the fatigue loads. So when, as it's a real model from a customer we have, this is there is a validation of this model. So they go to the lab and they test this part in 3 directions. And for example, the most critical direction for this component most of the time is up-down force, like we see here. So you apply the maximum for going up and going down, and this creates the cycle fatigue load. And also before this variation of load, we apply the bolt load in the simulation. So the first time step is the bolt load, and after that this stress variation. Here I show you some information about the material. For example, here we are using a ductile cast iron, and the yield stress is around 310 megapascal, and also the tensile strength around 448. So it's a material with a high yield stress, and this part is not very, it's a very engineering material. And here, by using FEMFAT, for example, we can generate the SN curve, which is the alternate stress in function of the life of the component. So, for example, in FEMFAT, we just select the material class, and the tensile strength of this material. For example, here we are talking about 448, and the material class is this ductile cast iron. So after this, FEMFAT generates this SN curve, which is used for the fatigue simulation. Of course, for example, if you don't want to give the opportunity to the software generate the curve, you can import from some tests, for example. And here is the endurance limit of the material, or the fatigue limit of the material, which is around 160 megapascal, which is high for this material, for example. So the first step, or I mean the second step for this project workflow was going back after we got the result of the simulation. We also generated this new design based on the new design that we got from Virtual.PYXIS during the optimization. And here, for example, Virtual.PYXIS is running together inside Ansys Workbench to generate this new design. So here is the design which we obtained from Topology Optimization, and here is the CAD interpretation. So you see the tendons was kept from this part to this. There are just some small modification considering the situation of the optimization, trying to get a better, most of the time, a better process or manufacturing simulation. And also, from now we go to the next part of the workflow, which is the static validation analysis. So after we have this new design, we go back and we apply again those up and down forces, trying to see if, for example, here there is some problem with the component. In this case, the static validation, the limit is the stress, the yield stress, which in this case is 310 megapascal. So it's obligated that you have for every part of the component, everything below this more or less 300. So here you see that everything is below this value, which is approved from static validation. So here I just show the up force, but you have the up and down force, trying to see, for example, if there is some variation. And also this up and down, sometimes you get some different values for the maximum principal stress, which is also below 310. And here you see some region of high stress. And from the principal stress, you see this is in green here around 150, which is positive, which means this attraction force for this region. And in the end, you see that this is, for example, the critical region for fatigue. So the standard procedure for simulate this fatigue situation, you use it not considering the constant stress and local material properties. So this constant stress we get, for example, as a residual stress from the MAGMA simulation, and sometimes you have compression and traction stress from some parts of the model. For example, if MAGMA gives me traction forces for this region, perhaps it's a bad situation for fatigue. If it's a low value, no problem, but if it's a high value, perhaps it's a problem. And because this also affects from this constant stress, which is a mean stress, you vary the amplitude stress. So if you have a higher value of this mean stress, this is not good for fatigue. And also, it's important to consider, besides this residual stress, you considering the local material properties. For example, in this case, you can import also a new tensile strength for every element of your mesh, and the standard procedure, for example, when you have a simulation, you consider that every element of your model is under a standard value of tensile strength, and also a standard value of the fatigue endurance. But when we get these properties from MAGMA simulation, you see that there is some variation from part to part. So here, from this presentation, I not go very deep in how to show this inside the softwares. But after the MAGMA simulation, there is a universal file, kind of text file, and for every element of this mesh, of this component, there is a new tensile strength, which is also generate a new tensile, a new endurance limit, which is the fatigue limit for the component. So there's a kind of correction. But for this first situation, you don't consider both the residual stress and the local material properties. So, for example, here, this is the first result after getting the static validation without considering the properties. And here you see, for example, the critical region. We are saying, for example, here, we are calling 100% just to keep as a computation of the value. But this, for example, is for comparing these results with the, for example, after MAGMA, we can have more or less if those properties are good or not for the component after using MAGMA properties. So here, the critical region is like this. There's just some part here, and here this is a stress concentration for the bolt. Also, there is some radius here, but this part is more critical than here. This doesn't mean that the component here is failing. We are just considering by the colors to say that, for example, here we have 100% of the safety factor. And after that, we compared about the new condition with manufacturing properties. So going to the MAGMA casting analysis, the first step, there was a change from machined to raw casting. So filling some holes of the component, for example, like here. And here we present you the first results of this MAGMA simulation. For example, we see here, for example, some hot spots around this region, which is not very far from the critical region that we showed before. I think from this video it's easier to see this liquid fraction. So this is the last part of the model which goes to the solidification. And because of this, when you are trying to get this process from the manufacturer, you see that, for example, it's a situation to add close to this region a kind of fit, which will also help about this condition. So if you go to the next slide, for example, here using the fit, you see that now it's much better, and the last part of solidification now is inside the feeder. So this is very nice and important because here I'm showing you a new design and pretty much different from the baseline design. I'm not showing you here the baseline, but it's very different, less weight. And today, this lightweight situation is you see everywhere. So sometimes you change your design, and you have to feel if this design is good also when you go to the manufacturing process. For example, also here from the MAGMA simulation, we see some shrinking porosity prediction, something about 15% here inside this part. But it's not really on facing on the surface which is critical for fatigue. So this porosity is not good for our model, but it's worse if you see this porosity in the same place of the critical stress for static analysis, for example, or fatigue. But here they are far to each other. The process data, just this slide to show you, For example, the curing temperature, for example, is 1,350 degrees. Chemical composition of nodular cast iron. This is the code of the component. So here you have all the components. Inoculation, standard estimation, good, 100%. And shakeout, 600 in the thickest part of the model. So this is a general overview of what was used in MAGMA. So MAGMA, again here you see important results, for example, nodal count. So here you can compare, for example, also fraction of Pearlite, which is generated from your model. So if you have Pearlite or Pearlite, sometimes you this gives a different material property from your model. For example, if you have formation of Pearlite or Ferrite, at the end you see that the tensile strength of these two components, microstructure components, are different. So this is important, very important to consider in this situation, because you can, after this variation of the tensile strength for every Pearlite or Ferrite, you can use this information, for example, to the fatigue analysis. This is what I'm showing you here. The main situation is getting the tensile strength. So here you see some variation. For example, for this region you are getting higher tensile strength, and for this region you getting lower tensile strength. So for example, from our critical region, it's around here, you have, for example, around 500, which is even sometimes, in this case, for example, higher than, just going back here a little bit, just to remember you. This is our material properties. So we have as a standard for the tensile strength 448. So if you don't consider any properties of the manufacturing simulation, you are not able to see this comparison between different parts of your model. You consider everything around this, for example, this number, but you have even higher values of the tensile strength. Depends on the microstructure formation of your model. So this is the information you feed PenFat to understand this behavior. So, but also before going back to the PenFat results, you also see here, for example, the foam-ISIS stress of the components. For example, some regions have higher foam-ISIS stress, and this is in the room temperature, and the room temperature, but also here consider after machining. For example, here you see some residual stress on your model, which sometimes with foam-ISIS is not very clear. If for example, it's tensile or compressive stresses. But for example, if you go to the maximum principal stresses, here is more clear. You see, for example, for this region, the critical region, you don't have a very high, for example, tensile stress, which are more higher here, for example, and here. So again, this is the result of the residual stress from the MAGMA, and we can import this into the fatigue analysis to considering to this behavior to the fatigue. And also the other is this stress tensile strength variation, which gives a variation of the fatigue limit, because fatigue limit and tensile strength for metals, they are related. Sometimes, for example, for a casting, being the fatigue limit around 30% of the tensile strength. For example, for steel, between 30% and 50% of the tensile strength. So if you have variations of the tensile strength, you also have variations of the fatigue limit. So, and after this situation, you go back here to the fatigue analysis, and you use these correction factors for the residual stress, which inside the software we call constant stress, and local material properties. And after that, you go to the last part of the workflow, which is the new fatigue analysis. And also, this is, I think, the most important slide, because here, for example, you can compare in two sides. For example, so sorry, I think here is it's wrong. This is I'd like to say without any fatigue. Consider, for example, the local material properties and then the residual stress, and here you consider both. And for example, without considering both factors, you remember about 100% for the critical region, and keeping the same scale, for example, considering the properties, residual stress and the variation of fatigue limit due to the variation of tensile strength, now we have got 116%, so 16% more than the original model. So this is, for example, gives you a possibility to sometimes to think about from the optimization point of view, to go a little bit further and perhaps get more material away from the component, because you have some you are in a kind of safety position here. So because now you are much better than this, so the right is much better than the left, because you are considering more precision condition for the material properties. So some conclusions here. I didn't show you the original model, but this is the new design. The lightweight condition was 30% less weight compared to the optimizer compared to the baseline model. From the static validation, there was just a lower stress compared to field stress, less than half of the field stress limit. For example, during the part solidification, you could saw a hot spot in the model, but it was solely very easily solved by adding some feeder. And also, we could saw some shrinkage porosity prediction of around 15%, but it happened in a not critical region, in mechanical critical area, for example. So by using the MAGMA properties, the safety factor was 16% higher when compared to the traditional method, which does not take into consideration those corrections. And as I told you before, as a final conclusion, this study we can, for example, show that you have, like, for example, a higher safety factor, or you can think about to, for example, to go further with your optimization and trying to get even more material away from this, for example, 30%. So this is the last slide. Now I have some time. If you can address some questions, you can use in the chat. Any question about the optimization, the fatigue? I hope that if also there's some question about MAGMA software, I can answer you. I'm not the expert on that, but I think I can try to answer you. So I don't see here any question. I'll give just 1 minute more. But as a summarize, yes, please. There's some question. I will wait. As a summary of this situation, my intention to present to you this today is remember that it's important when you are having, even without optimization, going to the static simulation or fatigue simulation. Sometimes you also, it's important to consider these properties of manufacturing. We are working together right now with MAGMA in Brazil, and also ANSYS channel partner EPPOS in Brazil, trying to get some automatic window for example, for an ANSYS user in Workbench to, for example, to import this, not just for the fatigue evaluation here, because here you saw just for the fatigue side that we import the MAGMA properties, but also in static analysis, for example, getting the variation of the young modules, which sometimes affect the stiffness, sometimes not, it do affect the stiffness of your components, and we are working on this situation. So going to the questions. Yes, about the algorithm used for the optimization. Here, with Virtual.PYXIS, we are using the optimally criteria, which is a very known algorithm for optimization. Yes, some comment from my colleague from MAGMA Brazil. In regions, for example, there is, for example, like this slide. When you, for example, when you don't have traction, for example, sometimes you can understand it's a kind of compressor, which is, in this case, is good for fatigue. One more question. If the residual stress from MAGMA can be mapped into ANSYS for static or transient analysis. We are doing, David, answer your question, we are doing this right now. And I hope in just a couple of weeks or some months, we will have this, we are working on an ANSYS ACT. So we will get this information from MAGMA. And I'm pretty sure about static analysis, also about perhaps transient analysis if you are inside ANSYS Workbench. So we will import this also for this static and transient analysis. As I told you before, for example, the young modulus variation from the MAGMA process. So keep in touch with us and we can share this with you if you use, for example, MAGMA. Yes, someone is asking if I am recording. I supposed to be recording this, and after that I can we send this this feedback questionnaire, and also you send the link to this this presentation. Really sorry that in the beginning we had this problem. This has never happened before, but there's, I think the most important we gave the information, and it's not compromising the quality of this presentation. I have two more questions here from Rorit. If the objective function is weight, what are the input parameters? So here we consider for the optimization, the objective was minimize the compliance, which is the same as maximizing the stiffness of the component. And the constraint is, for example, some weight reduction. For example, in this case, we kept around 30% of the component. So this, the objective function was compliance, minimal compliance. Yes, another, I think the last comment from our colleague Schmidt from MAGMA Brazil, and also more for the static simulation. Also, I forgot to mention, we had in the past also together with MAGMA Brazil some nice work, for example, comparing different, because when you are starting the optimization, you are free, for example, to use, if you are, for example, we are splitting from this up and down or to the lateral direction. So because you have to give the software, the manufacturer, splitting direction. And here we are considering a situation of up and down. But for example, with this case, with optimization, we also can consider other directions. And together with MAGMA, for example, you can simulate every condition. And at the end, you can, for example, see if, for example, splitting Y or X direction, you have better, for example, mechanical properties for some critical regions. So this is also important to mention, that you have this situation that you can investigate different splitting directions and also simulate with MAGMA and compare which one is better for both static condition, talk about stiffness, also for the manufacturing process. So I think there's no more question. Thank you everyone for joining this. I will share this presentation with you, some questionnaire for feedback, and also the record. Thank you very much, and have a nice day. See you.